Consider the physics of a main battery propellant charge. Its engineering purpose is not to shatter steel like a high-explosive warhead. Its purpose is to burn. It is designed to generate a massive but controlled expansion of gas that pushes a projectile out of a barrel at supersonic speeds. It is a fuel for kinetic energy. But this mechanism relies on a critical constraint. The expanding gas must have a clear path of escape through the muzzle. If you ignite that same propellant inside a sealed steel box deep within a ship, the physics change instantly. The controlled burn becomes a chaotic pressure spike. The steel walls of the compartment replace the gun barrel. The ship itself becomes the pressure vessel, and when the pressure exceeds the yield strength of the hull, the result is not a simple fire, it is a structural disassembly. This is the precise mechanism that killed the German battleship Gneisenau. This 32,000-ton capital ship did not die in a line of battle at sea. She did not sink under the guns of the Royal Navy in the open Atlantic. She died while sitting stationary in a dry dock in Kiel. On the night of February 26, 1942, the Royal Air Force launched a heavy bombing raid against the port. The Gneisenau was a static target. A single armor-piercing bomb struck the forecastle. This weapon was designed to defeat horizontal protection. It punched through the armored deck and buried itself in the forward propellant magazine for the turret designated Anton. The bomb detonation was the catalyst, but the ship destroyed herself. The magazine contained tons of cordite charges. When the bomb warhead triggered them, the propellant did not technically detonate in the way high explosives do. It deflagrated. This means the substance burned at subsonic speeds but generated gas volume faster than the compartment could vent it. The physics are similar to an internal combustion engine where the piston has seized. The gas expansion was trapped. It hammered against the bulkheads and the overhead armor. The pressure wave moved faster than the heat. It sought the path of least resistance. In a rare and catastrophic failure mode known as a turret jump, the pressure found its escape route upward. The main battery turret Anton was a massive assembly of hardened steel weighing hundreds of tons. It rested on a circular roller path that allowed it to rotate. The gas pressure beneath it became so extreme that it overcame gravity. The explosion literally lifted the entire turret structure off its bearings. It acted like a piston being forced out of a cylinder. The heavy assembly was thrown off its mount and slammed back down at a twisted angle. This is a level of force that is difficult to visualize. It requires enough energy to treat a main battery turret like a bottle cap. The human cost of this physics failure was severe. 112 sailors were killed in the blast and the subsequent fire, but the structural cost was terminal. The bow section was wrecked. The internal frame of the ship was warped by the thermal and kinetic shock. The watertight integrity of the forward section was compromised not by water pressure from the outside, but by gas pressure from the inside. The Gneisenau was technically still afloat. The dry dock prevented her from sinking. But as the smoke cleared on the morning of February 27th, the engineers looking at the twisted wreckage of turret Anton faced a stark reality. The ship was no longer combat capable. The hull was intact enough to float, but the primary weapon system was severed from the chassis. The German Naval Command was now left with a broken hull and a difficult choice. They could scrap her immediately, or they could attempt one of the most ambitious engineering conversions of the war. They chose the latter, and that decision would leave the ship in a state of limbo for the next decade. The decision to repair a damaged warship is usually a calculation of time versus utility. If the repair takes longer than building a new ship, it is illogical. But the German Naval Command looked at the broken hull of the Gneisenau and saw an opportunity to correct a fundamental design flaw. The ship had been built with 11-inch guns. In the escalation of naval armor, this caliber was becoming obsolete. It lacked the kinetic punch to penetrate the belt armor of modern heavy battleships. The bomb damage to the bow created a forced pause in her operations. The engineers argued that if they had to rebuild the forward section anyway, they should not just repair it. They should evolve it. They proposed a radical conversion. They would strip out the damaged 11-inch turrets and replace them with massive twin 15-inch gun mounts. This was the same main battery used on the larger Bismarck class. But this decision triggered a complex chain of engineering consequences. You cannot simply drop heavier turrets onto an existing hull. The added weight of the 15-inch guns and their barbettes would alter the center of gravity. It would push the bow deeper into the water, reducing freeboard and stability. To compensate for this, the hull itself had to be physically lengthened. The plan called for a new, longer bow section that would add buoyancy forward and balance the new load. This initiated one of the most surgical procedures in naval salvage history. In late 1942, the Gneisenau was not treated as a ship, but as a modular construction project. Workers descended on the forecastle with cutting torches. They did not just remove the damaged plating, they severed the entire bow. They cut through the frames, the keel, and the decks in a vertical line just forward of the main armor belt. The damaged nose of the ship was removed completely, leaving the battleship with a flat, open face. The plan was to weld a new prefabricated section onto this cut. It was a technique known as cut and cover, where major structural surgery is performed to alter the fundamental geometry of the vessel. For months, the ship sat in this vulnerable state. She was a headless giant. The logic was sound, but the timing was fatal. While the engineers prepared the new bow, the strategic situation shifted. The German surface fleet was losing favor with the high command. The resources required for such a massive reconstruction were needed elsewhere, specifically for the U-boat war. In early 1943, the order came down to stop all work. The conversion was canceled. The Gneisenau was now trapped in a worst-case scenario. She was no longer a combatant, but she was not yet a wreck. She was a dissected hull floating in a shipyard. The consequences of this decision flip were irreversible. The guns were removed and sent to shore batteries. The new bow was never attached. The ship was left as a stripped hulk. She had no offensive power and no watertight integrity at the forward break. To clear the dry dock for other work, she was towed east to the harbor of Gotenhafen, known today as Gdynia. This tow must have been a grim spectacle. A once proud battleship moving slowly under tug power with her main battery missing and her bow ending abruptly in a flat steel plate. She was moored in the quiet waters of the harbor, not to wait for repair, but to wait for the end. The engineering gamble had failed. The decision to upgrade rather than simply patch the bomb damage meant that she would never sail under her own power again. She had survived the bomb, but she would not survive the bureaucracy. By March of 1945, the strategic timeline for the German surface fleet had collapsed. The Soviet Red Army was closing the ring around the harbor of Gotenhafen. The city was evacuating. Everything that could float and steam was ordered to leave, carrying refugees and wounded soldiers west towards Germany. But the Gneisenau could not steam. She was a crippled giant without a bow and without main guns. She was dead weight. In a normal withdrawal, she would have been scuttled at her moorings to prevent capture. But the Naval Command had one final use for the thousands of tons of steel that remained in her hull. She would not be scuttled as trash. She would be deployed as a weapon of terrain modification. This is the engineering logic of the blockship. When a defending force cannot stop an enemy fleet with gunfire, they attempt to stop them with geometry. A harbor entrance is a bottleneck. It relies on a deep, narrow channel to allow heavy ships to pass. If you can place a massive obstacle directly across that channel, you effectively delete the harbor from the map. The obstacle does not need to fight. It simply needs to exist and be too heavy to move. On March 27, 1945, with the sound of Soviet artillery audible in the distance, the Gneisenau was towed to the entrance of the breakwater. She was positioned perpendicular to the channel axis. The sea valves were opened, and demolition charges breached the hull. She settled heavily into the silt. The superstructure remained above the surface, but the hull became a steel wall beneath the waves. The war ended weeks later. The city of Gotenhafen became the Polish city of Gdynia. The borders of Europe were redrawn, but the Gneisenau did not move. She sat at the harbor entrance like a fortress of rust. She was no longer a warship, but she was now a dominant feature of the local geography. For the next 5 years, the wreck existed in a strange state of suspended animation. She was a hazard to navigation, forcing merchant ships to maneuver carefully around her broken form. But for the people of Gdynia, she became something else entirely. She became a landmark and a destination. In the harsh winters of the late 1940s, the Baltic Sea would freeze solid inside the harbor protection. This created a phenomenon that provides us with one of the most surreal images of the post-war era. The ice became thick enough to support pedestrian traffic. Local civilians would walk out from the shore, crossing the frozen sea to visit the battleship. This is our fringe technical detail for this chapter: the ice bridge. It allowed ordinary people to walk right up to the armor belt of a Nazi capital ship. They could touch the steel that had survived the Channel dash. Photographs from this period show small figures standing on the ice next to the towering ruin of the superstructure. These images give us a sense of scale that ocean photos often lack. Against the flat, white ice, the Gneisenau looks less like a machine and more like a collapsed office building. This period of dormancy could not last forever. While the wreck was a curiosity for the locals, it was a stranglehold on the economy. Gdynia was a critical port for the reconstruction of Poland. A major harbor cannot function with a 30,000-ton blockage in its main artery. The decision was made to remove her, but this was not a simple tow job. You cannot just pull a sunken battleship out of the mud, especially one that has been purposefully wrecked to stay put. The hull was flooded. The bottom was likely suctioned into the sediment. The structural integrity was compromised by the original bomb damage, the cutting of the bow, and the final scuttling charges. The Polish authorities handed the problem to the Polish Ship Salvage Company. They were staring at a mountain of steel that had been designed to resist enemy fire and was now resisting the laws of buoyancy. When the Polish Ship Salvage Company took custody of the wreck in April 1950, they faced a hazard landscape that went far beyond heavy lifting. The Gneisenau was not just a pile of scrap metal, she was a loaded weapon. The ship had been scuttled during a combat withdrawal, which meant she was still carrying live ordnance. The magazines might have been flooded, but sealed munitions do not expire quickly. The wreck was also a tangled mess of sharp steel, jagged blast damage, and underwater obstructions. This brings us to the concept of the risk shadow. In any salvage operation, the danger is not distributed evenly. It is concentrated in the dark spaces where divers must work by feel. The Polish engineers developed a plan that relied on buoyancy recovery. This is a fundamental technique in marine salvage. If you can seal the holes in a sunken vessel and pump the water out, the ocean will lift the ship for you. It sounds simple in theory, but on a battleship it is a nightmare of complexity. The hull of the Gneisenau was perforated by sea valves, scuttling charges, and the original bomb damage. Every single one of those openings had to be found and sealed airtight. This work had to be done underwater in the murky visibility of a working harbor by divers wearing heavy canvas suits and copper helmets. It was during this phase that the salvage operation claimed its price. The work was grueling and dangerous. Divers were crawling inside the dark, flooded compartments of a warship that had been dead for 5 years. They were cutting away debris and welding patches over leaks. One of these divers was a man named Józef Kaniewski. We do not know the exact minute-by-minute details of his final dive, but the reports indicate a failure of his air supply line. In the era of standard dress diving, the air hose was the lifeline. If it was pinched, cut, or fouled, the diver was trapped in a suffocating silence. Kaniewski died in the line of duty, a casualty of the war that had supposedly ended 5 years earlier. His death serves as a reminder that forensic salvage is not a passive activity. It is a hostile environment. Despite the tragedy, the work continued. The engineers realized that the ship was too heavy to lift in one piece, even with the water pumped out. The upper works, the superstructure, the funnel, and the heavy armored tower were dead weight that contributed nothing to the structural strength of the hull. They had to go. The salvage teams began a process of topside reduction. They cut the ship down. They removed the massive steel tower that had defined her silhouette. This process is visible in the few surviving photographs from the era. In one image, we see a peculiar detail that counts as our fringe entry for this chapter. Standing next to the wreck on a concrete caisson, or perhaps part of the breakwater, is a small structure resembling a lighthouse. It is a jarring juxtaposition. The ruined blackened steel of the Nazi warship sitting next to a peaceful navigational aid. It underscores the transition of the harbor from a battleground back to a place of commerce. By September 1951, the hull was finally ready. The divers had done their work, the patches were holding, the pumps were installed, the upper weight was gone. The Gneisenau was about to become a ship again for the last time. This was not a restoration of glory, it was a functional resurrection. The goal was simply to make her light enough to float off the bottom so she could be towed to the breakers. The risk shadow had been navigated. The ordnance had been cleared. The cost in blood had been paid. Now it was up to the physics of displacement to see if the German giant would let go of the Polish mud. On September 12, 1951, the salvage engineers prepared to execute the final stage of the operation. The timeline was critical. The Baltic winter was approaching again, and the window for a safe tow was closing. The preparation phase had been a war against leaks, but the lift phase was a war against friction. The battleship Gneisenau had been sitting on the harbor floor for 6 years. When a flat-bottomed hull rests in sediment for that long, it does not just sit on the bottom, it becomes part of it. The mud creates a vacuum seal against the steel plates. This phenomenon is known as ground suction. It is a powerful retaining force that can require thousands of tons of extra buoyancy to break. The engineers started the pumps. The plan was not to lift the ship violently, but to lighten her until the buoyancy force exceeded the grip of the mud. This brings us back to the trade-off knife. If they pumped too fast, the pressure differential could collapse the patched bulkheads. If they pumped too slow, the hull might break suction unevenly. This was the moment where the decision from 1942 came back to haunt the salvage team. We must revisit the fringe detail of the bow cut. Remember that the German engineers had surgically removed the forward section of the ship to prepare for a conversion that never happened. This meant that Gneisenau was aerodynamically and hydrodynamically incomplete. A normal ship has a bow that provides significant forward buoyancy. It allows the vessel to lift evenly. But this wreck ended in a flat, vertical bulkhead. The center of buoyancy was shifted drastically aft. The salvage team had to calculate the trim with extreme precision. If the stern broke suction first, the ship would pivot on the cut line, driving the open forward end into the mud. If that happened, the delicate patch seals could fail and the ship would flood instantly, reversing months of work. The ghost of the canceled upgrade was now a tangible physics constraint. As the water level dropped inside the compartments, the hull began to groan. This is the sound of steel under tension as the load path shifts from the seabed back to the frame of the ship. The structure was remembering its shape. Then with a sudden release, the suction failed. The hull broke free from the sediment. The Gneisenau rose. She did not look like the proud raider that had threatened the Atlantic convoys. She was a rusty, truncated hulk covered in marine growth and mud. She sat low in the water, listing slightly. But she was afloat. The physics of displacement had won. The resurrection was a success, but it was a grim one. The ship was immediately taken under tow. There was no celebration of her return to the fleet because there was no fleet to return to. The destination was not a dry dock for repair. It was a scrapyard. The successful refloat simply meant that the Gneisenau could be moved to a location where she could be butchered more efficiently. The outcome path here is clear. This was a successful salvage operation, but its objective was total destruction. The ship had survived bombs, mines, and scuttling charges. She had even survived the death of her own divers. But she would not survive the industrial hunger of post-war reconstruction. The steel that had been forged to project German power was about to be melted down to rebuild Polish cities. 30,000 tons. That is the number that defined the final value of the battleship Gneisenau. In the world of marine salvage, there is a distinction between recovery and clearance. Clearance is simply moving an obstacle. Recovery is about value extraction. This brings us to the concept of forensic salvage. In this context, the ship is no longer treated as a vessel with a history or a soul. It is treated as a high-grade mineral deposit. The steel that makes up a capital ship is not ordinary construction metal. It is high-tensile naval armor forged to withstand ballistic impact. In 1951, this material was a critical resource. Europe was rebuilding from the ruin of the Second World War. The cities of Poland needed girders and reinforcement bars. The Gneisenau would provide them. The dismantling process was rapid and brutal. Once the hull was towed to the breaker's yard, it was attacked with oxyacetylene torches. The armor belt, which had been designed to deflect British shells, was sliced into manageable blocks. The internal machinery, the turbines, and the propeller shafts were cut apart and melted down. By the end of the year, the ship had effectively vanished. She had been transmuted from a weapon of the Third Reich into the infrastructure of the People's Republic of Poland. If you look at the buildings constructed in Gdynia or Warsaw in the early 1950s, it is statistically probable that some of the steel holding them up was once part of the Gneisenau. But there is a twist in this story. While the hull was erased, one vital organ of the ship survived. We must remember the decision flip from Chapter 2. When the conversion was canceled, the main battery turrets were removed. The hull stayed in Gotenhafen to die, but the guns were sent to the front lines. The number 3 turret, known as Caesar, was transported north to occupied Norway. The German engineers undertook a massive construction project at a place called Ostrad. They blasted a shaft 5 stories deep into solid granite. They installed the turret mechanism inside the mountain, creating a fortress that was impervious to air attack. This leads us to our final fringe detail, which is the afterlife of turret Caesar. This is not a rusting relic sitting in a park. It is a fully integrated mechanical system that still exists today. The turret weighs 800 tons. It includes the gun house, the rotating stock, and the ammunition hoists that descend deep into the rock. When the war ended, the Norwegian military took possession of the battery. They did not scrap it, they maintained it. For decades, the guns of the Gneisenau were kept in operational condition, pointing out to sea to defend a NATO ally. If you visit Ostrad Fort today, you can walk inside the mechanism. You can see the loading trays and the massive breech blocks. You can see the German engineering that was meant to dominate the Atlantic, now encased in Norwegian granite. It is a surreal experience. You are standing inside the beating heart of a dead ship. The survival of turret Caesar creates a strange duality in the legacy of the Gneisenau. Her body was sacrificed to build the peace in Poland, but her fist remained clenched in the rock of Norway. The story of the Gneisenau is not a tragedy of sinking. It is a case study in utility. Every part of the ship was used until there was nothing left. She fought as a battleship. She served as a floating battery. She acted as a blockship to deny a harbor. Her steel built a city, and her guns guarded a coastline for another generation. The ocean does not negotiate, and neither does the scrapyard. But in this rare instance, the engineering was so robust that it outlived the nation that built it and the war that destroyed it.